Good to go. Great. Welcome everyone to this panel discussion. We'll be discussing simulation to lab to reality, really trying to understand how we get these multi-robot systems working in simulation and then pushing them to reality increasingly so that we can achieve some exciting real-world applications. And I think it's a good debate to have. We've seen a lot of amazing research, and it's really, what do we do with all of this research? And today with me, I have a wonderful panel. So online, we have Russell Graves, who's from Mathworks. He's been invested in the intelligent transportation research field and has been working on distributed control architectures. We've got here Michael Otte, who's assistant professor at the University of Maryland College Park. He researches the design and analysis of algorithms for autonomous vehicles and robotic systems. And this includes motion planning for single and multi-agent systems, which is relevant today, and distributed algorithms that enable robotic teams and or swarms to pool resources to solve their common problems. And before being at UMD, Michael was at the Naval Research Laboratory at MIT and at University of Colorado Boulder. And then we've also got here Roderich Gross, who's a senior lecturer in robotics and computational intelligence and leader of the Natural Robotics Lab at the University of Sheffield. His lab does really exciting work on robot swarms and reconfigured robots, and created a cool method called Turing learning as well that I really like, amongst many other things. Having visited his lab several times, it's always really fun to see all the robots going around. So a lot of exciting research on swarm systems. And before going to Sheffield, Roderich was a visiting researcher at MIT and also worked at Tokyo Institute of Technology at Université Libre de Bruxelles and at EPFL. So a lot of great people. For those who don't know me, I'm Sabine Hauert. I'm an associate professor of swarm engineering at the University of Bristol in the UK. And my team engineers swarms across scales from nanoparticles for cancer treatment to larger robots that could be used for things like intralogistics or environmental monitoring. So that's our wonderful panel today. The way this will work is we'll broadly be looking at two different topics. One is really, how do we go from simulation to application? And then the second topic is going to be, the endless debate. Should we have something that's centralized or decentralized, or maybe even a hybrid? And so what I'm going to do is drive the discussion here. And then after each one of those portions, I'll turn to the audience for your questions online, because I've got this magical iPad here as well as in the audience, so that you can ask us your crunchy questions and maybe challenge us a little bit. So I thought we'd start with a bit of an icebreaker. So what are the applications that you're excited about? What do you want these things to do if we manage to go from simulation to reality? So maybe I'll start with you, Roderich.
Okay, is that working? Yeah, great. So hello, everyone. Well, the short answer, I think there's really no limit where you can apply multi-robotic systems. So anything you want to do with a single robot system, why not do it with multiple? Because you can potentially do more work at the same time. The one application I would like to throw in today is monitoring forest environments and like environments with trees. So there's a lot of scope for this. A lot of the landscape on Earth, I think 30% is covered by trees, and we need to monitor their health, and this becomes increasingly important because they can lock carbon, they are important natural resources. This is often done via satellite images and like flying with a plane over them, but we also want to understand the quality of the soil, like from the ground, and maybe that's an application where swarms or groups of robots can be used, and it's definitely challenging in terms of communication because you have change in vegetation and so on. We had discussed it earlier today. We had a lot of talks by Stephanie, for example, talk about intermittent communication, where you will, that's one application area where that will be relevant to address.
Yeah, monitoring the environment, very good one, Michael.
I echo that strongly, and I think more than just the applications, I think that when you have a bunch of robots running around that all have some computation on board, it makes sense if they can all use that computation to help solve their problem. So that's maybe a little bit of a twist on some of the things. Some people looked at some of this stuff, it's a twist on some of it. It's not just kind of centralized or distributed, but once you are distributed, how can you really optimize the computation of those algorithms? And we've seen some of that today. I think other problems that are very interesting with multi-robot systems is how do you, physically interact with the environment in a variety of ways. And Roderich had a number of kind of ideas on that already. I think manipulation with multi-robot systems is definitely kind of wide open problem at the moment, and very interesting.
Okay, exciting. Russell, did you want to comment on cool applications?
Yeah, I thought that the agricultural applications and sort of environmental health modeling is something they're monitoring, and something that we're really involved with. Here, we've had a number of our recent sort of success stories as far as our customers adopting things for agriculture. We have I think there's an autonomous tractor that was recently developed for I think specifically for wine. For those of you that are wine enthusiasts, I believe it's roaming the groves now. And just in general, as we see a trend towards, I feel like as we see a trend towards electrification, I know this has gone along in the past, as things become more electrified and we start putting more of these sort of EVs out into the wild, the autonomy really goes hand in hand with that electrification. And so it's very neat to see applications like that develop. And of course, as representing Mathworks, it's we do a lot of the sort of deploy into the field anything, that's kind of been our business since like the 80s, to get things that last mile to where they're actually functional and in the out in the wild and behaving and performing some task in industry. And that's it. So just any application that we see that's able to make it all the way into the wild is going to be really interesting for us to see. So
Great, thank you.
all very good.
Anyone from the crowd want to shout out applications we haven't covered that you care about? You don't really need to raise your hand. You can just mention the things that you're thinking of. One thing that I'm thinking of is intralogistics as well, and how we manage the full pipeline. This is something we were discussing with my lab last Friday, from fabrication to things that are personalized near to home, where you want to deliver them, getting them to the person, and then all the way to the end of life cycle of that product to recycling. Yeah.
Can I ask a question from panel regarding the cool application?
Sure, go for it.
So regarding environmental monitoring, what about energy consumption of the robots we put on, we put on to monitor the environment? Can it have some adversarial effect on actually, we consume so much energy and basically we don't do any good by putting more robots. So can you comment on that?
So you read our mind, because the follow-up question was going to be about COP26 and the fact that that was ongoing, and what are we thinking in terms of multi-robot system swarms in the environment. So do you want to address that question about maybe the environmental cost of potential swarms and maybe the benefits depending on how we use it? Who would like to start? Okay, go for it, Roderich.
I'm happy to go. That's a very fair comment. I really appreciate it. In today's talks, a few people touching on this aspect. So Maximilian, I think, talked about not just completion times, but distances that are traveled. We had Philippe were talking about the energy consumption, actually. So we need to talk more about this. And it is not just energy, but it's one aspect. We had actually Stephanie talking about when to communicate and what. So not just using it as an infinite resource. So we have to be more moderate to the resources. If you had swarms, let's say in a forest, is also about, does it have a negative impact on the wildlife there? Or obviously, does it make noises and so on? So we have to look more widely at the impact, and eventually, are the robots we have, eventually there will be electronic waste, presumably. So like from the whole life cycle point of view, there's much more work to be done.
Okay. Marcus, anything to add?
I guess, yeah, it's there's a lot of open problems there for minimizing power. I think that's a metric that sometimes, at least, in the motion planning side of things, it's easy if you have a distance metric or something like that to work into your problem. But if you're actually thinking about power consumption, there's a lot of maybe lip service paid to that, but it doesn't, the math is not always as straightforward for that sort of thing, where maybe you have a solar panel and you're recharging your battery at the same time or something like that. Interesting open problems, lots of work to do. I think another thing to worry about, I guess, I don't think that we should stop trying to put swarms into places where they can help with environmental impacts. But another thing that we need to worry about when we're doing that is, okay, what happens if they break down out there? Could we go get them? We don't want like the forest to be littered with dead robots. So incorporating some recovery in the event that things go wrong into the, planning algorithms might be something to look at as well.
Yeah. So having a system level view, does the robot help in the sense of the system at the environmental level, and what is its cost if it's left in the environment, and maybe new materials as well, making them more biodegradable or things that can be disposed of more readily. Thank you. That's an excellent question. Okay, so let's move on to the first topic about how we go from simulation to reality. And maybe just a first question for Mathworks. What are the simulation to reality challenges that you see in multi-robot systems? And what applications do you think would benefit from this trying things in simulation before you push them to reality?
So I may go back and actually reference that question to try to help answer this. And I think one of the key sort of difficulties is actually going backwards the other way. So going from, once you have it in sim, it's actually, we have there's a lot of tools out there, including our platforms, Simulink and MATLAB, that enable you to really build these models up and integrate domain expertise. So for example, we have a large suite of things that let you model power consumption and the electronic side of things to try to get a handle on, or at least better understand some of those impacts and, and what you might need to have in terms of resources available, but then getting that back out to match, making sure that that simulation matches reality. So getting the agent then deployed into the real world, that becomes the key challenge. So it's kind of making sure that that domain expertise is designed correctly, such that when you do get the agent out into the real world, the expectations that the simulation have set are matched by what you observe in the field, and then being able to continually sort of either integrate or update your model to make them better as you build, kind of go along this deployment pipeline.
And I think a lot of us feel that pain. Any other challenges of going from simulation to reality and crossing that reality gap, or just things in general that are difficult in that area? Michael, do you want to jump in?
Sure, thanks. I guess on this topic, which actually it's interesting that this has shown up in this panel, because we've also talked about it in a couple of different things kind of back home, but I often end up being the provocative person that kind of, is all doom and gloom. And the reason for that is I think that one challenge from an academic point of view, at least in the US, and at least as a younger kind of professor, is that coming up with a research problem that results in a new and better kind of pipeline or simulator that then is applicable to the real world is not necessarily easy. And I almost, I apologize to anybody who does work on that, because I think it's really valuable work, but I feel like it's almost a little bit of a thankless task in our community. And I think that that's one obstacle from an academic point of view, is figuring out if I'm, want a PhD student to graduate, they need to write papers on something. And it's an uphill battle to kind of say, I built a really good simulator, you should use it. Here's a paper on it. It could be done, but I really see that most of the time that we build simulators, it is in support of something else that we're trying to show. And because it's always kind of in support of this other thing, we maybe don't do it really, really, really well. And from my point of view, I think that is almost perfect, like for a company or an engineer to like solve that problem, because they have kind of different pressures. And if you could build the best simulator ever, you might have a ton of customers from the academics that would just like love to use it. So.
Yeah, Roger?
Yeah, so I have mixed minds about simulation perhaps as well. So on one hand, one question is, if you have a simulation, can you actually trust it, and what gives you the confidence that you can trust it? On the other hand, even if you do an experiment in the laboratory, that doesn't necessarily not mean it works in a different laboratory, or it works even in the real life. So that there's a similar problem there. There are certain things that are hard to simulate, like close physical actions where agents get into proximity, or even communication itself. I think we talk about this here at MRS, modeling communication channels, for example. So there's it's totally different from the game of chess where you just have certain moves and there's a perfect simulation in a sense, you can argue, right? But in robotics, it's about the real life. You have a wide variety of conditions that the robot could be facing in the real life, and simulations are great to some extent, but it's very rewarding if you try to test the solutions in at least the laboratory, but hopefully even beyond.
So maybe a show of hands. How many of you have designed your own piece of a robot simulator, or have had to do a lot of the implementation yourself? So quite a few, quite a few of you. So for those who are online, I'd say the large majority here have designed their own simulator for their own research purposes. And that's something where even in our team, they're designing different simulators for the same problem sometimes, just to, I think, to own it, not to own it in the negative sense, but to wrap their head around it and understand what's going on underneath it. And that's very different than in industry. So maybe back to you, Russell. Why is it different, the pipeline from simulation to reality in industry and in the research world, maybe in the pressures that they face, and maybe how we can bring those better together?
Yeah, that's actually a really interesting, I mean, it's a really interesting question in general. I'm not surprised to see the hands. I think I personally have also built some sort of simulation tool specific to a problem I was trying to solve. And that was kind of in my university experience, that was just kind of came along with the gig, because usually what would happen is the thing you were trying to test or whatever you were trying to push forward, that boundary of, of understanding in the specific field, all the tool sets that were available didn't quite have that one thing or that one feature that you needed. But when you get to the point of trying to, I don't know, put a car on the road or put a plane in the air, what typically, differs is I think somebody mentioned earlier, trust in the fact that that's going to behave the same way in a variety of different circumstances. So, the question you can ask yourself is, okay, in your current process or for your current simulation, do you feel comfortable, taking what you developed and saying that is going to work on $100 drone if it's a drone swarm? And if you're cool with $100, what about $10 million? So if the industry can't trust that to work on their $10 million plus drones, then it's, that's really not going to fly. And what, no pun intended. Then kind of the difference here is that we really need to have a process in place that enables you to be confident in that. And I'll give us a shout out here that that's something we've been in the business of for again since like the 80s here. So industry leaders such as BAE, Lockheed Martin, those guys are confident that if we build something in our simulation platform, if we have you have a controls algorithm that can be plugged into tools such as Simulink, they all speak Simulink, and it can be verified and code-generated and deployed onto one of their edge devices, one of these drones that's flying around, or some of their autonomous operations, then that's the sort of level of rigor. They're held to a certain set of standards that need to be met before they're confident in putting that in the air, so that it's not going to cause any undue harm.
Really interesting. So there is somewhat of a different value system in what people care about. There, it's about the resilience and making sure that it works, and in the research, it's about innovation, I think, and getting, being able to push the edge a little bit and trying to get some, which is why we often end up adding a little bit to our simulation tools. Yes, go ahead.
I just wanted to ask, with regard to simulation versus real, whether there's something special about this multi-robot work. So I would assume we're not necessarily thinking about $1 million platforms. I would think we're thinking about, lots of fairly low-cost platforms. So maybe that the sort of per unit kind of risk of breaking it is not high. I would assume, and I have a kind of feeling that we might be able to get further in simulation in this area than maybe in some other areas, like a very, very sophisticated single platform that you're developing. Definitely, you would have very tight tolerances on whether you'd let that out in the real world, but maybe not if it's 1,000 fairly cheap things. Does that
Right.
make any sense?
It does. So what are our requirements, I guess, for a simulation system to reality that's specific to multi-agent systems, and maybe some of the fact that they aren't the high spec robots that we might be thinking of otherwise. Do you want to describe your pipelines? How do you go from, like, what do you need in a simulator, and then how do you go from there to testing them in reality, just to make it concrete?
Yeah, so following Andy's comment, I was just thinking about a student. We had a master student, Jeffy, who tested something, I think, with robots, and then they tried to put it onto a particular microcontroller-based robot, the EPUC, and the program failed. Well, it was because there was an error that was just too long. The robot didn't have enough memory, but that didn't occur in the simulation. Right? So there's the physical constraints of the robot in terms of memory, delays. Also, they are not always captured realistically in simulations. And it would be great if there was more simulations where you can use exactly the same source code in the simulation and on the real platform, and that embraces all of these constraints as well.
I was just going to say, maybe the kind of feedback loop between the real world and the test could happen a lot more easily than if you've committed, again, $1 million into a platform. You figure out, oh, I need twice as much memory or
That's
something,
right.
and then you can fix it and try again. Right.
Yeah, I think that is a very good point. If we have inexpensive platforms or platforms we can repair easily, then the simulation is less. We use it maybe to debug some algorithmic details, and at least that's what I do. Right? I often in my lab go, kind of pure theory, easy high-level simulation, and then maybe straight to the real robots. And that also may be an effect in the robot systems domain, because simulating multiple robots, especially with a high physical fidelity sensor, is still very challenging. You can do it for 1 or 2 robots. If you want to do it for 100, all of a sudden now you're looking at quite a lot of computation if you want to do that accurately. So a lot of times it is just a quicker path to getting a prototype actually working in the real world to kind of jump quickly there, and the cost is lower for a lot of the platforms we use. If you break them, you can order new propellers or something.
And maybe to add to that, they also break in different ways. So it's not just the platform that breaks; they break in their behavior as a collective. There's so many other layers that help with that simulation aspect. So I agree. We also do low fidelity, high fidelity testing in reality. And when we say reality, it's still in the lab, right? It's not yet like in a living lab or in the outdoor world. So what would we need to achieve that? Do we need standards? Do we need more of these common simulators that we all use, or how do we build a common resource, basically? And if anyone in the crowd has ideas, and I'll take one question online as well. Anyone want to have a go? We don't know, I guess. We need a workshop.
Oh, sorry.
The simulators so sometimes we use simulators to evaluate a high-level idea, and sometimes it's nice if the simulator is not close to reality. It's very abstract, and you have a one-to-one match between the equations when you describe the system and the simulation, and the simulator kind of verifies to some extent that or the theory that should be correct and proven also works. But so sometimes there's a beauty in the simplicity and the abstraction, but it doesn't exactly help when you want to put something into the real world. And so having simulators, not everyone developing their own simulator can help with the second part, but it doesn't necessarily help with the first part. Like sometimes it's nice to develop your own simulator just to really understand inside out what's going on, but it will have maybe limited applicability to solve a real world problem.
I think a one-size-fits-all simulator is only going to be useful, in the lab if it is easier to get whatever I'm doing working on that simulator than it is to build my own simulator. And there's a lot of times where we say, well, I could get it working, let's say in ROS or something, but it will, for the fidelity that I need not that level of fidelity. I can do it much more quickly not doing that. There's also the paradox, wherever level you decide to make your simulator, it could be slightly more realistic where things break. So I had the experience recently of getting something working on a swarm, worked great, put it on the test bed, and then it was like, oh, the friction is actually breaking everything. So that's we should have modeled that, but we didn't. you had a really good point, which I think is getting your simulator to run the exact same code base as much as possible as the actual robot really is accelerating.
Just a single click.
Oh,
If
so
we go from simulation to reality. And to be fair, we do use a lot of common tools. So we use, mentioned Simulink before, MATLAB, Gazebo, ROS, Mujoko, which I haven't used. Has the multi-agent community used that, or it's mostly has anyone used that yet? Mujoko, which was just purchased it by DeepMind to give to the rest of the community. I think it's more the manipulation area. Unity, etc. So there are common tools that we do build on. Okay, one question online from Javier, which is a very good point about accessibility. Experiments with real robots take a lot of engineering resources, and even then the reproducibility across groups is low. Any thoughts on how we can make real multi-robot systems more accessible? Go ahead, yeah. Russell.
Oh, sorry. I'll give an answer here as well to go back and address a few things that I'm just trying to listen in, and everyone's got really good points so far. It's been really nice. So I think this question kind of harkens back to exactly what the other two gentlemen on the panel are just talking about regarding making sure that you're basically going back and taking a step-by-step approach to verify that, hey, the algorithm that I've designed, that I've tested maybe on these small scale, these again, you're talking about a ton of low-cost robots. They're working correctly. Now, how do we go from that to something that in the field, either the low-cost robots that we deploy are going to be resilient, reliable? Again, talking about avoiding leaving waste robots, or understanding how many robots per, I don't know, per 1,000, per 100 are going to fail, and how do we recover those? And how can we be sure that these things are all going to run correctly in the real world? And that's why I know that our solution to that for a long time has been to enable we have a lot of software in the loop and hardware in the loop testing solutions. So if you, for example, have an algorithm designed to control one of these swarm robots and you've built it inside Simulink, our platform can actually test it, run it remotely on the hardware, the actual board that's going to run the agent in the field. We have a lot of options for doing things like that, again, to verify exactly that point, that the code that you designed, the code that will be running on that device, on that edge device, on that little swarm agent, is going to behave exactly as it did in the simulation. And you can more easily better understand any limitations that you're going to run into and find these problems much earlier on. Because even if we are talking about tons and tons of low-cost robots, I mean, it's essentially the same problem as you have with automotive manufacturers when they have to, if they have to recall a very small part on a vehicle. That's still an enormous undertaking to then take all of those agents back and replace that bit to make sure that it's not going to, fail prematurely or endanger anyone. And so I think that's something that's really, really powerful, needs to be considered when you're talking about actually going from a lab into having these things fly through a forest or something similar.
Yeah, and I just want to make sure we answer Javier's question as well. In addition to that, how do we get hardware to people even if they don't have access to it?
So that's a very good point. So the one initiative I know is a Robotarium. You may have heard of, I think it's at Georgia Tech, where you can upload your source code and they let it run on some robots in their lab. They have a localization system. You can do kind of a remote experiment, and that proved very good, useful during a pandemic if you didn't have any access to your laboratory anyway. We need more of these systems. If you think about, if you submit a paper to a journal or conference, the algorithms, the model, the mathematics gets super high scrutiny, or should be, like at MRS. But on the other hand, the simulations and experiments don't really, because I can count on a single hand the number of reviews I've ever seen where someone has verified either experimentally or by simulation the results, by repeating, trying to do a simulation, like as a reviewer. And if there was something like the Robotarium, we can just share, okay, you can just try it out, right? And it will work. But this would give much more rigor into this, bringing to the real world, and that could help.
Yeah. And I know the UK is interested in ideas of proving grounds, so places you could go to test some of these technologies, a little bit like you go to CERN if you want to test something in that specific field. Maybe we need something like that for robotics. You had a question?
Yes.
Thank you for the discussion. I had a question about what you use in terms of simulation? Because I see there's like two extremes. Either you have a high level simulation that allows you to verify an idea, not to have to go through the hardware right away. And we've been talking about the kind of other extreme, which is I have my simulator that has a button, and when I click the button, I'm sure that what's running on my hardware is the same thing as in my simulator. But in that second case, I almost have to invest as much to make that work than if I had to run it directly on the robot. So I'm just interested in understanding what the community is doing in terms of simulation platforms, whether you go the whole chain or more on the simulators for a high level, or the simulator that goes straight to the hardware. Thank you.
And maybe this is the last question on this topic, and then we'll shift to the centralized versus decentralized. So what tools?
Do you want to start?
Sure, I'll go quickly. So we use ROS, we use home-built custom stuff, and it's really project dependent. And I think it's, again, from an academic, young kind of professor sort of point of view, it's completely driven by what do we think is the quickest time to actually get something fielded, and so then that just drives everything.
Not necessarily can give good answer, but like we have tried a range of tools from Argos, Gazebo, then custom made things using Bullet or ODE, and then the very simplistic 2D simulations get kind of grid based that we typically just write on ourselves, and WebBots or the 2D version of it we use as well. So we haven't been too systematic in it, I must admit.
Right. Okay. And we also have just a final comment from Mosin, who's asking, where do we put swarm in the loop? So not quite sure what the definition or the right term would be, but trying to understand what we should consider in terms of developing the platform. Where should we place it in the spectrum of sim to lab to real? So it's basically not having a full, if I understand it correctly, not full simulation or full reality, but basically having a closed loop control. And I think this also goes, I had a question about digital twins and just this closed loop reality between simulation, reality, and how do you go between back and forth to get better results overall. I don't know if Russell, you have any thoughts on digital twins and how you close the loop, and just very briefly so that we have some time.
Yeah. Sorry. We've tried to do that. We've been involved in looking at how to better create digital twins over the years. We're more recently looking into, I think, what the gentleman on the web was talking about as far as swarms, sort of digital twins of swarms. Right now, we've got a lot of expertise in the digital twins of single agents and single devices. And typically it involves understanding the proper instrumentation that you need in order to get the key characteristics that you're trying to analyze from the specific device. And then having a set of tools. We have a method for then taking those data that you're collecting from those sensors and feeding that back into sort of a system identification or plant identification workflow to parameterize and get the correct parameters for those physical objects in simulation.
Right, thank you. Any quick thoughts on that? Or okay, so the other topic we wanted to talk about was centralization versus decentralization, and I think it's a discussion we've been having for many years. And what's interesting now is I think there's maybe a convergence in the sense that centralization sees the potential for decentralization. And decentralization now has robot capabilities that are a bit better, that can communicate better, compute better, and maybe the need for pure, simple agents is no longer there. So what do you think is the right way forward? Centralized, decentralized, hybrid in the applications that you mentioned, for example? Who would like to, maybe Roderich this time?
All right, yeah, well, it really depends on the context in my view. If you have a bounded environment where some agents interact, like a logistics center, why not use centralization? So if it is affordable, if there are benefits, I don't see a reason against it if you are using it for a long enough time. If in other situations, I mean, think about, we just talked earlier, imagine there was Uber moving to driverless cars and you have like millions of cars around the world. Who would ever think about planning the motion of all of them centrally? I mean, it would be insane to get all the data into a single point. So that depends on the scale of the system, whether they are operating in a bounded environment perhaps, and so like from case to case, I can see advantages, disadvantages for both approaches, and one has to see what is, one thing is nice to do research where you compare the two, so where you see what is how much do you lose by implementing a distributed controller, right? So if you lose a lot, then maybe you should think about can you compensate this by making it centralized? Or, but if you don't lose much, then maybe you don't worry.
Michael?
Yeah, I think that it will be very problem dependent on kind of where we end up, and the problems could kind of be the same, except for we're now in slightly different settings where I have access to communication or I don't, or communication of a certain reliability. Maybe I would use centralized system to solve the problem if the computational complexity of the problem is such that that's feasible. There's always trade-offs. We've all read tons of multi-robot systems papers where, you know, we talk about the advantages and disadvantages of centralized versus decentralized, and I think that it's really dependent on the problem. But for my own work, I guess, like, if we are in the decentralized domain, I really like the idea that all of the robots can kind of pool in their computation to help solve the problem, which maybe is called, you know, ubiquitous computing in some other contexts. If we need a ton of computing power, though, like maybe we just, you know, put it on the cloud, like Stephanie was talking about in her talk. If you need that much computation, you can't really run that around on a little, you know, turtlebot or something like that. So again, kind of long way of saying problem dependent.
Yeah, problem dependent. And even in the applications, so for example, the logistics ones, in that centralized approach, it makes sense in many settings because you have the database, you understand where everything is, and you can imagine a big warehouse might like that. But in a messier environment, you might not have that infrastructure or the comms, or you have the constraints that change. And even within applications, you might need decentralization because you don't have access to the things that those larger warehouses have. Russell, did you have any thoughts on centralized or decentralized, or?
I said we're typically Mathworks is in the business of trying to be that sort of source for tools and things that you might use to investigate these problems. The other two panelists have an excellent point of view on this. I will mention really quickly. I almost forgot. We have a representative that should be on the ground there, Alessandro. And if you all are interested in or working towards developing solutions like this, I'd love for you to get in touch with him. We'd love to know about them because we're interested in making sure that, you know, you have the tools to sort of investigate these types of questions.
And you mentioned the computational resources, and I think there's also maybe a shift where we used to do machine learning in a centralized way, where we'd learn what the behavior was and then put that on the robots that were decentralized to see what would happen. But we probably have more capabilities maybe on the robots as well. So where should learning happen in this multi-robot world? Do you want to comment since you did interesting?
Yeah, it's a good question. So very often when we do research, at least in our group, we evaluate things on real robots only for a very short duration. And so that's not very practical. So if you test something for 10 minutes or at most 1 hour, whereas in probably real world applications, you need to have things running for weeks and months perhaps, and with recharging and so on. So, and then there's the question, so if you do one-off training and then you port something and it works in a static environment fairly nicely for an hour, that won't be sufficient for like a dynamic environment constantly changing. So I think ideally we want to have robots that can adjust to change of circumstances of different weather and all of this, different depleting battery. It's like we need to get better in the online learning domain. Yeah.
Great, Michael, any comments? And then I'll take a question from the crowd.
I guess the only kind of learning and swarm stuff that I did was a couple of years ago, but it was really the opposite of deep learning. It was very shallow learning on a swarm of kilobot robots that only, you know, transmit 9 bytes at 2 hertz to each other. But you're even able to get some advantage doing that. Again, problem dependent probably is the name of the game. If you have the ability to kind of distribute your learning kind of interaction stuff with the world on a bunch of different robots and have them kind of pool all of their experience, it seems like a really good way to parallelize, you know, and there was good paper, I believe, a number of years ago where they, you know, I forget the author, I want to say Sabine, but the arms training just basically had to grasp stuff over and over trying stuff, but that takes so much computation. So if you can, you know, you don't need deep learning necessarily to solve this stuff. if you can get away with really low cost, low power learning, maybe that's enough to solve your problem. Maybe that'll work on a swarm because we have more robots to kind of provide input.
Great. Mhm.
Would you think that apart from these technical reasons that depend on how cheap communication or computation is, and that might change over time, that also something like privacy could it be an issue and perceived independence of decision making? I mean that in both directions. On the one hand, that sometimes people or clients or agents want to make their own decisions, informed decisions, or that they don't want to share all their data, but also and that's an argument for our community, but also in the opposite side, because a lot of, if I think of big companies, they tell their investors, we earn money by collecting data and by making use of the data. Couldn't that also disincentivize to use a distributed algorithm, because they say, I wanted all the data on my server anyway. I don't want that some agent network does their own decisions and keeps some data for themselves to keep communication minimal. So would that also be a consideration?
Yeah, I mean, definitely. So privacy also unrelated perhaps, but like whether systems are vulnerable to attacks. Like I don't have an answer, but it would be a centralized system be more vulnerable than a distributed? Can you spoof and so on easier in a distributed or a centralized way? So yeah.
And I think it also puts the computation on the edge. So what you're describing also means that all that computation, the interaction with the user happens on the robot itself rather than getting fed back to a central controller. So there might be good implications there in terms of where your data is processed. Yeah. That also makes me think about, maybe we want a fake centralization, because human operators like centralization in the sense that they like to have this map, right? And this visibility of what's happening. So somehow we're going to need to take these decentralized systems and present to them something that looks centralized, even if it might not be. So maybe the hybrid, which was the premise of the question, might be a fake hybrid or a real hybrid, or I don't know. Any thoughts on that?
Yeah, hierarchical approach can make sense.
Yeah.
Right? So like absolutely. So like where, I mean, you mentioned earlier how much is known about the environment. If the environment is fully understood, maybe that lends itself more to a centralized approach, like playing chess in a sense. You have full knowledge of the board, you do decisions, and I'm not sure if we can do it easily decentralized, where every like the pawn and the queen, all of them move in a distributed way. That would be fairly challenging. But if you, as you said, like if you discover locally things, and that's local to one robot, right? They discover something, they can share it with a neighboring robot. So like where the information is already distributed, maybe there's stronger notion, and also where you have distributed manipulation tasks, and so it really depends on the task.
Yeah. Any last questions? Yes, over there.
Again, building up on what you said about privacy, I also wanted to introduce the concept about security, because we're also creating a network of computing agents and agents that make the decisions and then can autonomously transmit and receive data, but there's also could be the presence of malicious agents that could interfere with the functioning of the network. So like maybe there has to be put in place a certification system or authorization system, and that's often done in a centralized way. So translating into distributed, the distributed way might be also a challenge to take into consideration.
Yeah, good point. Do we have a chance in decentralized systems? Maybe.
I think that's an interesting class of problems to look at. How can you maintain privacy in your swarm of which agent, or entry into the swarm, maybe using tools from onion routing protocols or something like that. There's definitely people are thinking about these problems in other domains, and maybe we can start to incorporate them into our research to kind of find new and interesting twists on problems to solve.
And insects are very good at detecting self and non-self and agents that are sick. And so nature has found decentralized ways of doing that. We have to crack it. It's a very good point. Okay, so I think we're running out of time now, so we should probably wrap up. Final thoughts from the panelists. Are robots in the, or multi-robot systems in the real world, are we there soon? Yes, yes or no? Or maybe Russell to start. Hopeful.
Yeah, I'll be positive. I think at least from our perspective, the tool sets are sort of there. The testing framework is there. We need somebody with a mandate, and we need a good application and a mandate at this point. And I think we'll be right there.
Yeah, someone to drive it. That's a very good point. Michael?
Mixed but hopeful.
Oh, good.
Yeah, we are seeing huge progress in a number of applications, from logistic warehouses to manufacturing, surveillance, and it's using in entertainment like fireworks and so on. So, and it's moving on. So it will not stop there. It will move to, I don't know, healthcare and then in the hospital. These are where the privacy will be very important, as we discussed, and I think agriculture as well. There's so many places where it will go. I think it's just unstoppable. I think it's good to be doing research in multi-robotic systems.
So I'll say yes too. So real-time consensus formation, and I guess we all agree. So thank you very much for participating and for your questions, right, Amanda? Thanks, Russell.
Thanks.
Thank you. Take care, everyone.